Hello, everyone. In this video, we will introduce heap sort. Heap sort uses a binary heap. It first adds all the elements to a heap and then removes the largest elements successively to obtain a sorted list. Heap sorts use a binary heap, which is a complete binary tree. Additionally, it has this second property, it's called the order property. Each node is greater than or equal to any of its children. A binary tree is complete if every level is full except the last level. On the last level, all the nodes are placed leftmost. This is a complete binary tree. This one is also a complete binary tree, but this is not, because this should all put leftmost. So this is not leftmost. There's a one spot open right here. This is not binary, complete binary tree, because right here, this is unfilled. Every level should be filled except the last level. Those two are the complete binary tree. Are those two also a binary heap? Let's examine the order. 42 is greater than all this, and this is all in the right order. So this is in the correct order. It's a complete binary tree also. Everything is in the right order. So this is a heap. However, this is not, because 42 is greater than 39 though. So this is not, it is a complete binary tree, but it's not a heap. Let's look at this animation to see the heap. You can add 45 here. So when you add 45, you put 45 right here. So this is fine. And let's add 55. 55 is going to be here. Put 55 going to be here. It is a binary tree, but it's not a heap. The order is not right. So we're going to go swap 55 with 11, then with 43. So that it will make it a heap. How do you store a heap in your program? Visually, it is a binary tree. When you store in the program, you can use an array list. Put the numbers level by level. 62, and then 42, 59, 32, 39, 44, 13, 22, 29, 14, 33, 30, 17, 9. So put it level by level in this order. From this storage, you can identify the relationship for each node here. Look, this index 4. Who is the parent? You can compute it using this relationship here. For a node at a position I, its left child is at position 2i plus 1. So here's 4, and this is 9. its right child is at position 2i plus 2. So this is right here. That is exactly right. So here, 14, 33. Now, who is the parent? The parent is the index I minus 1 divided by 2. So here's for 4. 4 divided by 1, 4 subtract 1 is 3, divided by 2 is integer division is 1. So the parent of 39 is 42. You can look at any of this note. For example, look at 9, 13. Who is the parent of 9? It's 13 minus 1 is 12, divided by 2 is 6. So it's right here, 13. This is at index 13, and the node is 9, and the parent of 9 is 13, right here, 13. The index is 6. Now, it's not difficult to discover the relationship because it's a complete binary tree. So the way you allocate all these elements in the array list, and this will guarantee the relationship. It's easy to discover. So you don't have to add additional information in the data structure. You can derive it through the index. You find who is the left child, who is right child, and who is the parent, and using really simple calculation to find it. Now, how do you add a new node into the tree? Let's look at this. I'm going to add 3. Initially it's empty, so put 3 right here. It's the root. Now add 5. So when you add here, you're going to add 5 right here, the next level, the first one. And then see who is the parent of 5, 3, comparing this with 3 and see whichever is larger is going to be put to the top. Now let's look at it here. You are going to put 22 now. So you put a 22 right here. Think about the data structure. It's array list. You put 22 at the end of the array list, and to find the parent of 22, that's 1. And now, not in order, swap it. And then find the parent of 22 to 19, not in order, swap it. So that's how you do this. When you do this, add a new node to a heap, that's how you are going to process. First, put the node in the right position in the array list, and then find its parent and comparing with the parent. See if you need to swap and continue all the way until it's in the right order or it becomes the root. Now, how do you delete a node? When you delete a node, you always delete the root. Root is the largest number. You delete this and it becomes an empty spot. So you move the last 9 to replace it. And then you can find who is the left child, right child. Compare all this number, find the largest one, and swap it with the root if necessary. So continue to do this. Now here, let's put the 9 right here. 9, 42, 59, 59 is largest. Swap 9 with 59. So 9 is here, and swap it with 44, and then swap it with 30. So that's what eventually you will see and here at the right here. We have now the algorithm for adding a node, for removing a node, and we are going to put everything into this data structure called the heap. So we're going to have this heap. This heap, it's the, we're going to have this, all the elements in the heap now. So in the new addition, we are going to have just, this is a heap with the E. And then we add a new constructor. You can specify the comparator. And you can also put this, the comparator as data field right here. So those are the constructors and the method for add, remove, and get size. I'm going to stop here, and in the next video, we're going to come back to review this class, and we're going to implement it, and we analyze the complexity, and we'll give a heap sort algorithm. See you on the next video.